So in the previous lecture, we have introduced so-called S-metrics, and we have shown that it's a special limit of the evolution operator in the Dirac representation, namely it's a limit from time TIF to minus plus infinity of the Dirac evolution operator from time Ti to time Tf. And we have found that the solution for the corresponding object can be obtained in compact form. The t-ordered exponential minus I and integral from minus infinity plus infinity dt from the interaction Hamiltonian in the Dirac representation. That means the interaction Hamiltonian in Dirac representation is t-dependent, and it differs from the interaction Hamiltonian in the Schrödinger representation by just e to the minus h0t, where h0 is the free Hamiltonian. And in our quantum field case, the interaction Hamiltonian in the interaction representation, the Dirac representation, can be obtained from the interaction Lagrangian, from the density of the interaction Lagrangian up to the minus sign. And we supposed that this interaction Lagrangian depends only on the fields, but not on their derivatives. And if we insert in this interaction Lagrangian, the classical interaction Lagrangian, the Dirac representation of the fields, we obtain just the interaction Hamiltonian in the interaction Dirac representation. We have proven several important properties of this S-matrix operator. One of them was unitarity. And we have also shown that the S-matrix conserves energy in the sense that the S-matrix commutes with the free Hamiltonian. We have also decomposed this S-matrix into the T-matrix, so the part which doesn't correspond to any interaction and the part describes the true interaction. And we have also shown that provided we calculate the matrix elements of this S-matrix in the states which are eigenstates of the free Hamiltonian, so some eigenstates initial and final, which corresponds to energies initial and final, then the S-matrix is non-zero only in the case when the initial energy is the same as the final energy. And this allows us to write for this S-matrix, for this matrix element, between the final eigenstates of the free Hamiltonian and initial eigenstates of the free Hamiltonian as delta corresponding to the energy conservation. This corresponds to this part of the S-matrix, plus, and we conventionally add here some normalization, times delta function expressing the conservation of energy, and something which we called T-matrix corresponding to the transition from the initial to the final state. And this E-matrix was just on the energy shell and was function of energy. It was the same for the final and initial energy. Okay, in fact, this formula is nothing else but the infinitesimal form of the statement that S-matrix is invariant with respect to time translations, which are generated by the free Hamiltonian. Of course, on our Fock space, on which all this dynamics takes place, we have also other generators of the Poincare group, namely the free momentum corresponding to spatial translations, the angular momentum operators corresponding to rotations, and the generators of boosts. So it is a nature question whether this S-matrix is the operator which is invariant with respect to the free representation of the Poincare group. Therefore, our next task will be to prove that, in fact, the S-matrix is invariant with respect to the complete representation of the free Poincare group. Okay, let us refer to our formula for the S-matrix as a t-ordered exponential corresponding to I insert this Dyson expansion, and we obtain here just integral over whole Minkowski space d for x of the interaction Lagrangian, which is in the Dirac representation. That means it will depend on this interaction fields in the interaction representation. So this we will call L interaction in the Dirac representation depending on spacetime X. And as we noted when we discussed the construction of interaction Lagrangian, the interaction Lagrangian should be as an operator, as a classical Lagrangian should be scalar, and as an operator, this Lagrangian should transform as a scalar with respect to Poincare transformations. So we suppose that under the free representation of the Poincare group, this interaction Lagrangian transforms as a scalar. That means that such a sandwiching of this Lagrangian density corresponds to the transformation of this argument. Fine. So naively it seems that everything is okay since this Lagrangian is scalar, and of course this measure in this formula is also invariant measure with respect to Lorentz transformation, so that it seems that the S matrix might be invariant. But there is some subtlety which is connected with the fact that we have here T product. Of course, if we rewrite this, expanding this exponential, so if we rewrite it as infinite sum and goes from 0 to infinity, I to the n over n factorial, and now n integrals d for x1 up to d for xn from the T product of the corresponding Lagrangian densities. Then, if there were no T product here, in fact, this formula, together with invariance of this product of the measures on the Minkowski space, would guarantee the invariance of the S matrix, in the sense that this U0 lambda A on this string of these operators, U cross lambda A, inserting just unity between these operators in the form of cross 0, would give just transformation of the string or of the corresponding, so D, of this string of operators in transformed spacetime points. But this is the case of the ordinary product of the operators. And then, of course, we can transform also these measures and we obtain invariance. But, so this is our ask to prove. But, should prove just this statement. But when we have here the T-ordered product, there could be problems, since these transformed arguments of this invariant Lagrangian could have their zeros component and T components rearranged. Since we know, then in fact, the Lorentz transformation can rearrange the order of times. But when it is possible on the, if we have two space-time points, say x1 and x2, then provided these points are spatially separated, that means if this square of this difference is smaller than 0, then this is the case. Then it can be found a Lorentz transformation, then provided x1 0 is say smaller than x2 0, it exists a Lorentz transformation that x1 0 primed transformed is greater than x2 0 prime. So there is a problem. In fact, we obtain something like this, since always we can identify this T product with some order product of these Lagrangians. But provided we sandwich this string of these operators with these operators ensuring Lorentz or Poincare transformation on the Fock space, then the resulting string need not be arranged in such a way that it is T-ordered in the new primed variables. That means these variables, the 0 component of this transformed space-time, can have different order and not the order in which the x0 is the smallest one and the x prime 0 1 is the largest one. So how to escape from this rearranging of the times? Now we know that a very important requirement in our theory was the requirement of causality. And causality was a property of our field operators, of the free field operators, that means the field operators in the Dirac representation. states that, for instance, for scalar fields, such a commutator was zero whenever this x and x primed were space-like separated, and provided this is the case. Therefore, in the cases when the Lorentz transformation can rearrange times, in fact, the arguments from which we construct the building blocks from which we construct the interaction Lagrangian, that means the Dirac fields. Therefore, even if there is some Lorentz transformation which arranges the times in such a string of operators, we can arrange them back in the proper order to be arranged in the primed times, simply using this commutation relation. So, in fact, the causality and the causal properties of our fields is the key property which ensures the Lorentz invariance of the T product, provided the operators, which are T-ordered, are causal. And this is the case since we constructed our interaction Lagrangian from the causal fields. Of course, in the case of the scalar fields, there is commutator. In the case of fermionic fields, we will see that there should be anti-commutator. So this is just either anti-commutator, or commutator. But we will see that this is enough to construct the Lagrangian density as a causal object. That means the Lagrangian density will satisfy the necessary condition. The necessary condition for invariance of the S matrix. That means the commutator of interaction Lagrangian in two spatially separated points is just zero. Okay, so we can conclude that S matrix is invariant with respect to Lorentz transformations, provided we use the free operators. That means with respect to free representation of the Poincaré group on our free Fock space. Of course, we know that whenever such a, so to say, global relation is satisfied, then also its infinitesimal form is satisfied. And infinitesimal form means that the S matrix commutes with all the generators of the Poincaré group, this zero index, that means all generators of the free representation of the Poincaré group. We have already shown that it commutes with Hamiltonian, but this implies also that it commutes with free momentum, that it commutes with angular momentum, and that it also commutes with the generators of the boosts. Namely, these two means that S matrix in fact commutes all the translation generators, that means with for momentum. And in the same way as we proved that S matrix preserve the energy, we can also show that S matrix preserve the for momentum. We know that this P0 is just the same as P for interaction. So either we take eigenvectors of the free for momentum, or for the or free three momentum, or the interacting free momentum, everything will be the same. So let us suppose that we calculate the matrix elements of the S matrix eigenstates of free for momentum. That means we have some P mu free states with initial and final momentum, and it will give just the corresponding eigenvalues. And then again making such a matrix element of this commutation relation. This is of course P0 free representation of this P mu I. This should be zero. On the other hand, this should be the difference between Pi minus Pf times the matrix elements. It's matrix between these two states. And therefore we again see, provided this is non-zero, then this must be zero. So we can repeat what we did for the energy conservation, and we can write the S matrix elements between these free for momentum eigenstates. And what we get is just this delta Fi, which is nothing else but such a scalar product, plus, and again conventionally we put here some normalization, 2 pi to the fourth times I times delta function, now expressing the conservation of for momentum, Pf minus Pi, times something which we could f TFI, and this TFI is sometimes called the T matrix on the form momentum shell. Okay, these relations or invariants of the S matrix with respect to free representation of the Poincare group have also some other consequences. The one consequence is the so-called vacuum stability. What happens if we act with S matrix on the Fock ground state? The Fock ground state is defined as the only states in our Fock space which is invariant with respect to the all Poincare transformations, and therefore this Fock space should be, for instance, annihilated by the form momentum p mu 0. So let us try to calculate what happens if we act with this p mu 0 on S on vacuum. Due to the commutation relations, this one, we can write it as in the different order, S to p mu 0. And of course, this is 0. This is one of the defining property of the vacuum state, the Fock space. So this is 0. So this is 0. And the same can be done also for the other generators, for the generators of rotations and for the generators of boosts. So we see that from vacuum, we can create a new state, which is again invariant with respect to all Lorentz transformation, all Poincare transformation, in fact. And since the vacuum in our Fock space is unique, it cannot be nothing else but vacuum up to some phase. Let us denote this phase alpha. So the S matrix lets the vacuum states intact, and in fact, it is useful to remove this phase. And instead of the original S matrix, take a new S matrix, namely E2 minus I alpha times the original one. This is not equality, this is replacement, times the original S matrix. That means, since we can calculate this phase, simply sandwiching this S matrix with vacuum, since we know that vacuum is normalized to 1. So we can redefine this S matrix, dividing it by its vacuum expectation value. And in fact, it is useful to this, since as we will see later, this removes some irrelevant part of the S matrix, namely so-called contributions of the vacuum Feynman graphs. So in fact, this so-called rephasing of S matrix or redefinition of S matrix allows us to omit completely some sort of Feynman graphs. Okay, the second property is related to one particle states, and it can be stated as stability of one particle states. Suppose we have some one particle states which are characterized by their form momentum and some discrete quantum numbers, charges, spins, and so on. And we will ask what happens if we act on this state by the S matrix. So suppose that these states are kinematically stable. That means that in the spectrum of the theory, there are no particles to which such a particle, one particle states, can decay kinematically. Simply, there are not possibility to have some other multi-particle states. In such a case, that the energy of such multi-particle states is the same as the energy of this or form momentum of the multi-particle states, the same as the form momentum of our one particle states. So this is not the case. That means the particle is kinematically stable. But then, acting again on this state with the free form momentum operator and using the commutation relation, we can again rearrange it, so write it in such a case. And since this one particle state is eigenstates of form momentum, this just gives the corresponding form momentum times S times K sigma. And again, since these particles, one particle states are kinematically stable, and we have seen that this S times K sigma is again something which is eigenvector of form momentum with the same value of the of K, with the same eigenvalue as the original one particle state. It cannot be nothing else but again the one particle state with the same form momentum. Of course, if we return back to this situation, I was a little bit cheating here, since in fact, provided we have particles with zero mass, then if such a particle has zero momentum, then it also gives zero value for the form momentum. So in fact, this should be taken with care. But since this S matrix is unitary, it preserves the norm. And such a one-particle state, which would have the same for momentum as vacuum, that means 0, 0 for momentum, would have completely different normalization. So in fact, this proves the previous statement also with this subtlety. Okay, let us also explore our S-metrics a little bit more in a little bit more detail, and let us show that in fact such S-metrics can be constructed from much more simpler building blocks called so-called connected parts of S-metrics. These connected parts of S-metrics intuitively are connected with the scattering processes in which no subsystem of the particles in the initial beam do not interact independently on some other subsystem. I will explain it just after giving you the definition of the connected parts. Simply, let us calculate the matrix elements of S-metrics between some final and initial states. And the definition of the connected part is such that this metric element is in fact sum over products of much simpler matrix elements called connected S-matrices or connected parts of the S-matrices, which are the matrix elements between some clusters which are included in this final state and in this initial state. Let us explain you what I mean. Suppose that the initial state is a state consisting from 3 particles. This is 3-particle state, suppose they are scalars, K1, K2, and K3. And in such a system of 3 particles, we have several clusters or subsystems. One such subsystem is just the system of all these particles, K1, K2, K3. But there could be other subsystems which consist of 2 particles, K1 and K2, and isolated 3rd particle. And of course, permutations, that means K1, K3, and isolated K2, and K2, K3, and isolated K1. So we divided this system of 3 particles in the 2-particle cluster and 1-particle cluster in all possible ways. And of course, there is also one cluster in which all these particles are isolated, K3. So let us denote this cluster as E1, this cluster as 2, and so on. The same can be done in the final states. And now this product here over all clusters in the initial state and in the final state. And the sum is over all the composition of the initial states in the clusters. So we take, for instance, 3-particle cluster in the initial state. And if we have similar decomposition in the final states, we, for instance, take 2-particle, or it's not the best example, but suppose there are 4-particle, for instance. So we take 3-particle cluster and 0-particle cluster, so on. 2-particle cluster here, and so on. Probably it will be better to draw some figures, some pictures. Suppose, I will draw the picture a little bit later. Let us take a look at this formula. In fact, this formula can be taken as a recursive definition of these connected parts of the S-matrix, in the sense that provided all the connected parts of S-matrix with smaller number of particles in initial and final states are already defined, then this SFI is just the connected parts which corresponds to the simple clusters where all the particles in initial states are in one cluster and all particles in the final states in one cluster, plus something which corresponds to this sum over the remaining decomposition of initial state and final state in the clusters, but with smaller number of particles in each cluster. And we need also some initial condition for this recurrence, and this initial condition is just the situation when the initial and final states are 1-particle states. Therefore, the initial condition is just as 1-particle cluster, and 1-particle cluster is just the scale product of finite particle state, initial particle state. So this is just our invariant delta function of kf minus ki times probably some other delta functions corresponding to other quantum numbers describing these one-particle states. So, and now the promised pictures. So we can start with just two one-particle states, and let us denote this S matrix element such a figure. These external lines corresponds to the particles in the initial and final states. And as we have seen, if the initial and particle state have just one particle, then this is the same, the connected part. Sorry, should we see? This is the initial condition for this, and we have to fix just the connected part of this simple situation. So we have such a relation. Provided we have four particles, that means two particles in the initial state and two particles in the final state, then according to our prescription, it is just the connected part corresponding to two particle cluster in the initial state and two particle cluster in the final state, plus the product of S matrices when we decompose the initial particle states, final particle states in the clusters. So here it is just the possible sum over all permutations of the corresponding initial and final states of just the connected part of the S matrix with just one particle in initial state and one particle in the final state. And of course, this sum is over all the possible labels at these external legs corresponding to all possible combinations of the initial one-particle cluster with the final one-particle cluster. Let us try to explore the situation when there are three particles in the initial state and three particles in the final state. Then, according to our recursive formula, it is just the situation. In initial state, we have three-particle cluster. In the final state, we have also three-particle cluster. Then we can have sum of permutations of the external legs corresponding to the case when we have one particle cluster and two particle cluster in the initial state and one particle cluster and two particle cluster in the final state. Again, over all the possible permutation between these two legs, that means between the combination, between the various cases, how to decompose the three particle states into two particle cluster and one particle cluster. And of course, we will have also sum over all the possibilities where we take one particle clusters, the initial states, and one particle cluster in the final state. Again, all possible combinations of the clusters in the initial state and in the final state. So this picture suggests that the interpretation of this connected part of the S matrix is just that this connected part describes the true interaction of the subsystems of the initial state and final states, and there is no other decomposition to the subsystems in these connected parts. That means the connected parts describe the situation where all the particles which are in the initial states and in the final states interact together. There is no independent subsystem, as in this case. There is 2x2 scattering and 1-to-1 scattering. There are no such subsystems in which some subsystems of particle would interact independently on the rest. Okay, from the definition, we have seen that these connected parts corresponding to interaction on independent subsystems factorize in the complete S matrix. This is one feature. And the second feature is that we will see later that these connected matrix elements, as a function of momenta of the ingoing particles and outgoing particles in the process, are in some smooth, but in parentheses, in the sense that they have not singularities like delta functions, no delta function singularities. Besides the only delta function which corresponds to the expression for momentum conservation. Therefore, such S matrix elements, connected S matrix elements, or so-called S matrix elements of the connected S matrix, is just this delta Fi, as we have seen, plus I 2pi to the fourth times delta 4 of Pf minus Pi, expressing the conservation of the momenta, times something which we call Tc Fi, the connected part of the T matrix, and just this function, Tc Fi, has this smoothness property. There are no delta function singularity in this object as a function of taken as a function of the external momenta. In fact, there are some singularities. There can be poles, there can be branch cuts, and so on, but such severe singularities as delta function are absent in such a object. And in fact, just these objects describe the true interaction of the initial and final particles. There are no non-interacting subsystems. And therefore, what we will be interested from now on is just this TCFI matrix elements. Once we know these matrix elements, of course, we can reconstruct the complete S matrix using this formula. These matrix elements are just building blocks of the complete S matrix. Okay, so this was the theoretical properties of our S matrix. And now we would like to connect these objects to the observables, namely to the decay width and cross sections. That means something you directly measure in the experiment. So we have seen that the initial states for our scattering processes are some wave pockets, which are superpositions of multi-particle states in our Fock space, which are the eigenstates free for momentum, which are described by 4 momenta and some discrete quantum numbers. Of course, we should be careful since these eigenstates are smoothed by some wave functions, and we have also demanded that these wave functions are such that if we evolve these states back in time using the free Hamiltonian, the corresponding wave pockets should be not overlapping, and the particles should be spatially separated, and they therefore do not feel each other and don't interact. We could make such a careful analysis using these wave pockets, and only then we can make realization, and these wave pockets, which we denoted as K and sigma, to replace by delta functions in the momentum space corresponding to some initial or final momenta. But we will be a little bit less careful here, and we will do such a formal limit from the very beginning. So our assumption will be that we will be interested in matrix elements of the S matrix between just such a multi-particle states. Well, let us remind you the resolution of identity on our Fock space. Suppose we have only type of the particles, for instance, one type of scalars. So we obtain just projection on the vacuum state, and then projections to the n particle states, which can be due our normalization of n particle states written in such a way. This is a normalization factor which is related to our normalization, and here is integral over dk1 dk2 over the invariant measure on the mass shell times the state k1 kn k1 kn. This is the completeness relation for our multi-particle states on the Fock space. Okay, so this is resolution of identity, and provided we are interested in measurements in the final state, in which, say, these momenta of the final particles, k1 up to kn, are in some finite set in the space of 3 momenta. From this, obtain the projector which corresponds to this area of the space of the momenta, just as 1 over n integral over this dki times this k1 kn k1 kn, and we integrate just over the region in the space of the momenta delta. This is just our space. Okay, so this is the general projector which can be used for measurement. Suppose we have some finite region in the space of the momenta, and we would like to calculate the probability that we measure particle momenta just in this region of the space of the momenta. So we know that if we know such a projector, we can calculate the corresponding probability simply taking this projector and sandwiching this with the corresponding outgoing state. With the corresponding outgoing state, which we can obtain just by acting on the incoming state, on the initial state, with our S matrix. Or, since we suppose that the initial state is completely orthogonal to the final states, we can use here, instead of the complete S matrix, the T matrix. Instead of the T matrix, we can use the connected S matrix, since we are interested in the true interactions of all the particles in the system, and we cannot allow some partial interaction of the subsystem. And of course, provided this initial state is not normalized, we should normalize it. So this is the general formula you know from the quantum mechanics. Simply, we evolve the initial state to the final state after the experiment when we do the measurement. That means we act on this initial state with this T matrix, which evolves this, since S matrix is something like time evolution operator. And with such a state at T goes to infinity, that means far after the scattering process, we simply sandwich by this state projection operators which represent the measurement. And the projection operators which represent the measurement is given just by this and correspond to the measurement of the momenta of the particles in some finite region delta, our space of the momenta, or phase space. Okay, this is the case of the finite region in the space of the momenta, but we can also write this formula infinitesimally, simply rejecting this integral and write it as in differential form, simply as just this matrix element. This we obtain if we elaborate this sandwiching of initial state with the state and its operator. This is the normalization. And then you have this normalization 1 over n factorial correspond to the case if all these particles are the same sort. And of course, this product invariant measures over the momenta. This is the formula. So we have something which allows us to calculate the infinitesimal probability, which describes the scattering experiment in which the initial state I, evolves into the final state, which is the multiparticle state of particles with momenta k1 up to kn. Of course, such a matrix element, which we need for calculation of the probability, is nothing else but the matrix elements of the connected part of the T matrix. And if we suppose that also the initial state is an eigenvector of the free form momentum, therefore the initial state is some multiparticle state described by some momenta corresponding to free states in our Fock space, then we calculate the matrix element between the eigenstates of the form momenta, and therefore, according to our representation as matrix, this can be given just by this 2 pi to the 4 conventionally times I times delta function expressing the conservation of the momenta times this curly TC Fi, which is just the matrix elements of the connected part of T matrix on shell, on the momentum shell. And as we noted, just this is the smooth function in the sense that there are no delta function singularities, so we have only such a delta function in front. Okay, but we see that it is problematic to make a square of modulus of such an amplitude just because of this delta function. We have to calculate something like square of the delta function. If we multiply any function by delta function, that means that we should insert in this any function the solution of the delta function. So in fact, what we get here is 2 pi to the 4th times 1 delta function, pf minus pi, and again 2 pi to the 4th times the second delta function, in which we insert the solution of the for the argument of the first delta function as a 0. We obtain here, delta 4 at 0 times the square of the modulus of this smooth, in parentheses, connected part of the T matrix. Okay, but we have some experience how to deal such objects, since we know that this 2 pi to the 4th time delta 4 function at 0 can be understood as the limit for k's go to 0 times the integral representation of this delta function. That means d for x times e to say plus I k times x. So formally, this is the integral over d for x. And what we did when we meet such expression was to make an infrared cutoff. That means to place our system in a box, and here also to limit the time. Therefore, we can regulate this, taking the integral of, say, minus t half to t half over dt times integral over some finite volume d3x. What we get here is just v times t. So in fact, formally, we can write this tp to the fourth times d4 0 as a limit for v goes to infinity, t goes to infinity, like this 4 volume of our Minkowski space. Okay, so inserting this to our formula for the differential probability, we obtain that this dpf I can be written as just this v times t. Well, we have here this normalization times this and this. That means 2 pi to the fourth delta 4 pf minus pi times the square of the connected part of the T matrix, and now times the product of Lorentz invariants, the Lorentz invariant measures corresponding to the momenta of the particles in the final state. Okay, this is the key formula, and there is useful to denote just this and this as a new measure, the Lorentz invariant phase space corresponding to n particles. Well, I have probably missed here this 1 over n factorial. And this Lorentz invariant phase space is just defined as a measure on the space of the momenta in the final state times this product of the Lorentz invariant measures. Well, why it is Lorentz invariant? It is Lorentz invariant because just these measures are Lorentz invariant, as we have already explained. And of course, this delta function is Lorentz invariant object. So this measure is Lorentz invariant, therefore it can be calculated in any frame, any inertial frame you wish. To be more concrete, this Lorentz invariant phase space, of course, is a function of this initial momentum. And since it is in fact Lorentz invariant, it can be a function only of its square. Let me give you some example. Such a Lorentz invariant phase space for 2 particles can be calculated if we saturate these delta functions by integration over some variables which are contained in this integration, and the result can be described as follows. It is the momentum of the part of the to be more specific, suppose that in the final states we have 2 particles with masses m1 and m2, and if we are in the rest frame, in the so-called center of mass frame, center of mass system, in which the configuration of the final states is such that the momenta of the particles in the final states, k1 and k2, that's up to 0. Therefore, we have a situation when particles have the opposite momenta. Then the value of these momenta, absolute value of this momenta, is in this center of mass system the same. And let us denote it as, say, K center of mass system. And this can be calculated, and you will do it during the exercises in the seminar. And you can calculate it using so-called Chelin triangle function. This is a function of 3 variables, a, b, and c, which is defined as a squared plus b squared plus c squared minus 2ab minus 2ac minus 2bc. And value of the free momentum, the absolute value of the free momentum in this center of mass system, can be expressed in terms of this triangle function of Mandelstam variable s. Mandelstam variable s is just the k1 plus k2 squared, which in center of mass system where the spatial free momenta adds up to 0 is just 4 times sum of energy of particle 1 in the center of mass system plus energy of particle 2 in the center of mass system squared. Therefore, this s variable is nothing else by the complete energy of this 2 particle system in the system center of mass. So free momentum is just such a function of the variable s and of the masses to the 1/2 over 2 times square root of s. And now this Lorentz invariant phase space can be written in terms of this k CMS. Here is some 4 pi second times square root of this variable s times the element, of the space angle in the CMS system. This delta m CMS is just d phi times sine square d theta in the spherical coordinates. Okay, so this will be calculated as an exercise in the seminar. This is just some trivial integration, since you can see that these delta functions are simpler in this center of mass frame. So some of the integrations here will be trivial, and what remained as unintegrated is just this element of the special angle. Okay, so we have derived the following formula for this Fs v times t over I. Now 2 pi to the 4th delta function of, we can now simplify it using our Lorentz invariant phase space. So just FIC modulus square times this Lorentz invariant phase space for this n-particle finite state. This will be our master formula, from which we will now try to derive the observables, namely the coefficients and the decay wave. So we see that these T matrix elements or connected T matrix elements are crucial in calculation the probabilities or something which is measurable. Okay, so suppose now that we are interested in the process when some particle of mass m decays into some final state. And this final state is some multi-particle states corresponding to particles momenta k1, k2, and so on up to kn. And also some discrete quantum numbers are here. We will not write them explicitly. So such a decay process corresponds to the case when the initial state is one particle state which is created from the vacuum state by some creation operator corresponding to the momentum of the decaying particle and some spin or other discrete quantum numbers. And if we try to calculate the norm of this state, which is just part of our formula, we are again in problem, since we know that such a state is normalized to invariant delta function, but now the invariant delta function is at 0, since the momentum of this state is the same as momentum of this state. Therefore, this is delta 3 at 0. But we know how to treat such an expression. Again, we use this trick with Fourier transform, and we see that this is nothing as a limit for v goes to infinity. Oh, sorry, it should be. So it is just twice this energy times this volume. Okay, so this is fine, since if we insert it in our master formula, we cancel this v in the numerator with this v in the denominator from this normalization of the state. And what remains is this t, which should also be taken to infinity when we, in the end of the calculation. But what we can calculate is just so-called decay rate or partial decay width, which corresponds to decay of the particle m to the final state m, which is defined as the probability pfi recalculated to unit of the time, so dpfi over t. And this is just the expression which is finite in the limit when t and v goes to infinity. So what we get is just 1 over n. I have of course forget this symmetry factor, provided we have n particle final state. So 1 over n is this symmetry factor, and this decay width is defined provided we are in the rest frame of the decaying particle. So in such a case, the momentum of the decaying particle is 0, and the energy of the decaying particle is just this mass. From this norm, we obtain here 1 over 2m times this square of Fi times differential of Lorentz invariant phase space corresponding to n particle final state. So this is the partial differential decay width, or also decay rate. And this is the formula which is independent on this T and V, and T and V can be taken to infinity, so the regularization which we have used can be removed. Okay, so this is the differential partial decay rate. We can, of course, integrate this to calculate the partial decay rate, which corresponds to all possible momenta of the particles to which this initial particle decays. That means this is this 1 over n factorial 1 over 2m integral over this Lorentz invariant phase space from this T C F I squared. Of course, we can also make some generalization of these two formulas. Suppose that there is not only one type particles in the final state, but several types of particles. And in such a case, the projector operator from which we initiated is in fact product of corresponding projector operators of the different types of the particles. So we have its own factor 1 over n factorial for each number of particles corresponding to different sorts of particles. And therefore, this differential partial decay rate can be written as a product over all the sorts of the particles. And F is number of the sorts of the particles times 1 over n alpha factorial. Alpha is number of particles of type alpha times this 1 over 2m, again this T FIC squared times Lorentz invariant phase space of particles which are, this n is just sum of number of particles of types alpha. Okay, if we have the partial decay rate, we can calculate the total width. The total width is sum over all admissible final states. And of course, this is nothing else but 1 over T, where T is the lifetime of the particle. Okay, so this was the decay width or decay rate. And what about processes where two particles collide? So we have one particle 1, particle 2, and these particles collide and produce in the final states some multi-particle state F. In such a case, we again start with our master formula, and we have, in this case, calculate the norm of the initial state. The initial state now is state corresponding to two particles, P1 and P2. And so the norm is just, as we know, provided these particles are boson of fermions, 2 pi to third times 2e1, 2 pi to the third 2e2 times three-dimensional delta function of P1 minus P1 times delta function P2 minus P2. This is one term, and the second term, which corresponds to the pairing of the other creation, the pairs of the creation operators, and depending on the case whether the particles are bosons, this corresponds to this plus sign, and the fermions, this corresponds to this minus sign. The second term here will be just 2 pi to the third times 2e_p1 times 2 pi to the third times 2e_p. But now the different pairing between the momenta P1 minus P2 times delta 3 P1 minus P2. Okay. This can be simplified if we suppose that P1 is different from P2, so this second term is absent, and get here just delta function and 0, and again delta function and 0. So we can use again the trick with the finite volume and conclude that this norm squared of the state is just product of these vectors. That means 4 times energy of particle 1 times energy of particle 2, and this is just the volume, and it is the second power here. Okay, so this is our regularization of this norm of the initial state, and we can now insert it in our master formula, and we obtain just, master formula is here. So what we get is just that differential probability of this process corresponds to 1 over n factorial. This is the normalization corresponding to indistinguishable particles, times this Vt over the norm, and this is now 4 times V squared times 1 over energy of particle 1, energy of particle 2, times Tcfi squared times the Lorentz invariant phase space. Okay, this is our formula. We can see that we can cancel this V. Fine. So let us keep in mind this formula. And now how the differential cross-section is defined. Okay, suppose that we have a scattering experiment in which we have NP particles in the beam. This number of particles in the beam. And suppose that we are in so-called laboratory system, in which from the 2 colliding particles, 1 is in rest. So, say P1 is 0 and P2 is non-zero, and this P2 will have absolute value, which we call P lab, laboratory. Okay. A typical scattering experiment is that this particle at rest corresponds to some target, and let us suppose that we have NT particles in this target. So this is number of particles in the target. And suppose that this target has a geometrical area A. So this is the area of the target. Then the differential cross-section is defined that the number of scattered particles from initial state to the final state is just proportional to number of particles in the beam, number of particles in the target, times just this differential cross-section over the area of the target. That means this has some geometrical meaning. We can to each target particle associate some area, which corresponds just this differential cross-section Fi. And if there are NT particles in the target, then the complete area which is associated to this NT particles is just the sigma Fi times NT. And the complete area of the target is just A. That means this is just some geometrical probability that the 1 particle in the beam hits the effective area corresponding to these target particles. Okay, so if we have NB particles in the beam, then of course we have NB times larger probability than the beam particles hits this effective area of all the target. And the number of reactions is just given by this probability times NB. Okay, so this is the definition of the cross-section, and we can calculate the number of particles in the beam simply provided we know the current JB, which corresponds to the number of particles in the beam for unit area and unit time. So if the experiment lasts time t, this is just the number of the particles which can hit the target during the whole experiment. Okay, so we can see that inserting this to our defining formula, we see that this sigma Fi, the differential cross-section, is just this number of reactions over NB over NT times A. And therefore, if we insert this to this formula, we obtain just dNFi over this current, JB, times T times NT. NT is number of target particles. And now back to our formula. This formula describes idealized case when we have just one target particle and we have the current which corresponds to one particle over the whole volume V times the velocity. This is nothing else but the density of the particles, and we have just one particle in the volume V, so this rho B is just 1 over this volume V. And this current, as you know, is just the density of the particles times their velocity. But we can calculate this velocity since we know the momentum of the particles in the beam. We know that this velocity is nothing else but the momentum. That means the laboratory momentum of the particle in the beam over the energy in the laboratory. So this is the velocity. So in the end, we obtain that our current JB is just 1 over E times this P lap over this energy of the incident particle. And now this D and Fi can be identified with our dPFi. Okay, so inserting this to our formula for differential cross-section, we just obtain this 1 over n factorial times T over 4V energy of the particle 1 times energy of the particle 2 times this T Fi connected squared times just these factors, that means 1 over this JB, this is 1 over V, times this laboratory momentum over the energy of this particle 2, this is the laboratory energy of this particle, times this T, and T is 1, and what remains is just this Lorentz invariant phase space for the n-particle final state. So we see that we can cancel this T, cancel this V, and this is okay, since then the regularization can be easily removed. And in fact, the target particle was at rest. That means its energy is just its mass, m1. This energy is just this energy of the incident particle. So what we get is just 1 over n factorial, this TFIC squared over 4. What remains here is laboratory momentum times the mass m1 of the target particle times the Lorentz invariant phase space corresponding to n particle final state. Of course, this is our result. Of course, it seems that it is not much relativistic invariance. This is invariant. This, in fact, you will see that this invariant, but what is not invariant is this. But we can rewrite this, since this P lap times m, it is nothing else but, this small m1, it is nothing else but m1 times square root of the energy in the laboratory system of the particle in the beam squared minus m2 squared. And if we insert this m inside the square root, we obtain m1 squared times E lap squared minus m1 squared, m2 squared. And this we can interpret in the laboratory system as the scalar product of the form momentum of the particle 1 times the form momentum of the particle 2. Since particle 1 in the lab system has just such a form momentum, it is at rest, and this particle has the form momentum, this E lap, and P2, which has the absolute value equal to this P lap. Okay, so we can rewrite this in a manifestly invariant form as P1 times P2 squared minus M1 squared, M2 squared. So we obtain something which is manifestly invariant over 4 times this square root, P1, P2 squared minus M1 squared, M2 squared, times the Lorentz invariant phase space corresponding to n particles. Again, provided there are more than one type of the particles, this 1 over n factorial should be replaced by the product of 1 over n alpha factorials for each type of the particle in the final state. Okay, so we have several run out the time, so I will finish here.